Good morning all, this is Swapna. Welcome to machine learning video. Today's our topic is K nearest neighbor learning. This is the one of the approach to achieve the instance based learning. So we already know in the introduction, instance based learning is generally uses the memorizing technique. What is the memorizing technique? Is whatever the data given to the algorithm as a training data, it stores into the memory and it retrieves whenever the new instance classification is required. So that is the memorizing technique. Here in K nearest neighbor learning also it uses the same technique. So this algorithm assumes all the instances are corresponding to the points in the n-dimensional space. So in this algorithm, all the instances whatever may be given as a training or whatever maybe you are giving as a new instance to classify, that all the instances are represented in the form of points in the n-dimensional space, and the nearest neighbors of an instance are defined in the terms of a standard Euclidean distance. How it can in nearest neighbor learning, it finds the nearest neighbor instance for the new instance. To classify the new instance, it uses the measurement Euclidean distance to find the nearest one. So let an arbitrary instance x can be described by the feature vectors. So instance is described by the feature vectors. That vector is represented with the AR of x. AR attribute x related, the attributes related to the x instance denotes the value of rth attribute of every instance x, and then the distance between the two instances. Here xi is one instance and xj is one instance. The distance between the two instances is defined in the form of d of xi comma xj, where AR of x attributes of particular x, particular instance are a1 to how many number of attributes are using, or how many number of features are using to represent that particular instance, that are represented like this a1 of x to an of x. So to find the distance, Euclidean distance factor, to find the distance by using this formula, square root of r iterates r, AR x of I minus AR x of j square root of that one. So summation of all the attributes, summation of difference between all the attributes of xi and xj square, and totally we are taking the square root of that one. That is, we can call as a Euclidean distance. By this you are finding the nearest neighbor one. So in nearest neighbor learning, the target function may be the either discrete valued or real valued, discrete valued or continuous valued. Here we are considering as the discrete value target function. It is represented in the form of f of r of n, r to the power of n tends to v. V is the finite set of v1 to vs. What are that? What we can say? V means values of the classification or values of the target functions. K nearest neighbor algorithm for approximating the discrete value target function is shown in the form of f cap of x of q. X of q is the new query instance returned by this algorithm, as it estimates of f of x of q in most common value of f among the k training examples nearest to the xq. Xq is our new instance or new query instance, we can say, to find out that one classification and value of the target value of that new instance by using the nearest neighbor. Here f cap of xq means it is returning the value of that new query. How it is estimating that value means the training examples which are nearer to that one, within that it takes the most common value. Within that it takes the most common value. If I am taking the k value as 1 means it finds the one nearest instance. If k value increases, depending upon the k value, it takes the that number of nearest training examples, and what is the most common value within that. That is assigned as new target value. That is assigned as target value for the new query instance. So operation of the k nearest neighbor algorithm for the case where the instances are here, where the instances are points in the shown in the form of two-dimensional space, and the target function is Boolean valued function that we are considering here. Here the positive and negative training examples are shown. Two classifications are only there in training examples, positives and negatives. Positives are shown in the form of plus, negatives are shown in the form of minus. So here if you are considering one nearest neighbor algorithm, classifies the new instance as a positive example, and if you are considering 5 nearest neighboring algorithm, it classifies the new instance as a negative example. How it is given as a positive for 1 nearest and a negative for 5 nearest algorithm, here I am showing in the form of figure where the points training examples are seen. This leftmost figure, all the training examples are represented as a points in the two-dimensional space, and positive training examples are represented as plus, negative training examples are represented with a minus. Our new query instance is XQ. So whenever you are going for the just one nearest neighbor algorithm, then it finds the which is nearer one first, means for X this is the nearer one training examples. What is the value of this one? Positive. So it classifies it as a positive training examples. Whenever we are going for the k value increases. Here in this example we shown k we are taking as a 5 values. So we need to consider the 5 nearest training examples for the new query instance. Our new query instance is XQ here, and 5 nearest are this one, this one, this one, this one. So these are the 5 nearest training examples for the new query instance. In this, which one is the most common one is negatives. 3 negatives are there, 2 positives are. So most common one is negative. So that's why this new query instance is classified as a negative training examples. That's what here we saw. That's what here we specified. If you are considered one nearest neighbor algorithm to classify the XQ, it is given as a positive example. If you are considering the 5 nearest neighbor algorithm, it classifies it as a negative training examples. So what the impact general function is, or what the classifications would be assigned if we were to hold the training examples constant and query the algorithm with every possible instance in X is represented in the form of algorithm. This is the training algorithm. For each training example, x comma f of x. Add the example to the list of training examples. The training examples are represented like this: x comma f of x. X is the instance, f of x is the target value of the instance. How we are classifying? Classifying algorithm is given in the form of these statements. Given a query instance is represented with the xq, it is to be classified. Next, take the let x1 to xk. Denote the k instances from the training examples that are nearest to the XQ. Depending upon the K, that many number of training examples nearer to that XQ we are considering. How we are considering, and what is the classification of this new training example is that is represented with the F cap of XQ. And how we are getting this? We are taking considering all the training examples, and if the delta of A comma B is equal to 1, if A is equal to B, where delta of A comma B is equal to 0, otherwise. That means whatever the new training, most common training examples are, that many ones will come. So in previous example, whatever I shown in the figure, there are 3 negatives are there. Means whenever it encounters the negative, that is 1, 2, 3, it encounters the plus, it will count as a 1, 2. So which are having the more one, that is our new classification for the new query instance. So algorithm is shown in the form of steps. Generally, what is the definition of algorithm? Steps of the process that are shown here. K nearest neighbor algorithm is shown like this. First, within this first part is training algorithm. What is the training algorithm? How it is represented, and what is the twist of it? To classify, what is the first required? New instance. After that, whatever the nearest neighbor instances are there, within that which is the most common one, that we are returning as a target value of the new query instance. So this is the k nearest neighbor algorithm for approximating the discrete valued function. And here already told you, this is the figure representation. As here for this example, it to get taken as a two-dimensional space, and all the training examples are taken as a points. And in this example, there are two types of examples are there: positive training examples, negative training examples. Positives are shown as a plus, and negative training examples are shown as a minus. And here second figure, right hand side figure is, this is the, on the right is the decision surface induced by the one nearest neighbor algorithm for a typical set of training examples. The convex polygon surrounding each training examples indicates the region instance space closest to that point. Here this polygon is representing that which the nearest space to this training example. Every training example is shown as points here in this also. This one is one training example, this one is one training example, this one is the one training example, this one is the one training example. Here it is shown in the form of decision surface. What is how to we can take as a decision which is nearer to that, means the new whenever the new instance comes, if the new instance fall in which polygon region, that space it is considering as a nearest to this training example. If my XQ is fall in this region, then I am considering this training example is nearest to that. If my training example XQ is fall in this region, then I am considering this one is the most nearest one training example. So that one we can considering as a closest one, remaining all farthest one. If we are considering only the one nearest neighbor algorithm, this is the simple thing. So where the XQ falls, within that polygon, whatever the training example is there, that is considering as a nearest one. So next, the shape of the decision surface is induced by one nearest neighbor over the entire instance space. The decision surface is combination of convex polyhedral surrounding by each of the training example. That's what we saw now for every training example. The polyhedron indicates the set of query points whose classification will be completely determined. That's what I said. Whenever you are going for the new query points, if it is false in that polygon, that finding or that what is the value of the target value of that new query instances, whichever the training examples target value is there in that polyhedron. This kind of diagram is often called as Voronoi diagram for set of training examples. Whatever the representation here we shown right hand side of the figure, that type of representation, that type of diagram we can call as Voronoi diagram. This diagram is called Voronoi diagram for set of training examples. Generally it is represented for one nearest neighbor algorithm decision surface space. Voronoi diagram. The K nearest neighbor algorithm is easily adapted to approximating the continuous valued target functions also. Whatever we saw till now, that is related to the discrete valued functions. It can also suitable for the continuous value target functions. To find that nearest training examples which is nearer to that new query is here by using this type of formula for this continuous value target function. There we took the measurement is Euclidean distance. For here continuous value target functions, to find out the nearest training example, this is the formula. And this already we know, f cap of xq means target value of this query instance. How we are finding? By using this type of formula. What is the k value here? How many nearest neighbor examples you want to consider? That is k. Within this only, one more thing we need to know. Distance weighted nearest neighbor algorithm. What is distance weighted nearest neighbor algorithm? Already we know K nearest neighbor algorithm is to weight the contribution of each of the K neighbors according to their distance to the query point and giving greater weight to closer neighbors. So here to understand that one which is nearer to the training examples easily, here we are assigning some weights which is very clear, very near, very closer to the query point, that is having the more weight. that is having the more weight. So for example purpose, which approximate the discrete value target function, we might weight the vote of each neighbor according to the inverse square of its distance. For discrete value target function, if you want to assign the weights, what is the formula we are using to assign the weights is this one, Wi is equal to 1 by dr of xq comma xi to the power of square, that is inverse of squared distance between the new query point to that training example. That is the weight assigned to that particular instance, which is nearer to this query point. And what is the target value? Once again here we are adding in between this weight also. That one most common one, which is having the most weight, that training example target value is given as a target value for the new instance here. To accommodate this case, where the query point xq exactly matches the one of the training examples xi, and the denominator is like this, is therefore 0. If it is exactly matching that one, it will become as a 0. Then we can assign directly whatever the target value of xi, that is this. If there are several such training examples, we assign the majority classification among them. If more training examples are there, like that, whatever we saw previous example, that is what are the most frequently target values there, that is we are assigning. And this formulas are for the discrete value target function. And here we are giving the one more to find out the target function. One more, what is this one means? For the continuous target function, this is the formula to get the classification of new instance query. So summation of this one, here we are considering weights. So in the above variants of k nearest neighbor algorithm, consider only the k nearest neighbors to classify the query point. Once we had the distance weighting, there is really no harm in allowing all the training examples to have the influence on the classification of xq. In k nearest neighbor, we said we are assigning the weights to the nearest neighbor one only. If you are considering all the training examples and assign the weights for all the training examples, which are present on the instance space according to the distance between the distance from the xq to the training examples, then also no problem. There is no harm, because depending upon the which are having the largest weights, that are only we are taking. And the only disadvantage, if you are considering all the training examples, to classify our new examples slowly, is it will take the more time. If you are considering all the training examples, that is the main disadvantage. And if all the training examples are considered when classifying the new query instance, then we can call algorithm is a global method. If you are considering only the nearest training examples, then we can call it as a local method. To classify the new query instance, if you are considering all the training examples, then this algorithm is called as global method. If you are considering only the nearest training examples to classify the new query or new instance, then we can call it as a local method. So, is that clear? I think. And also, whenever you are considering all the training examples, and if you are considering as a global method, this is also have the one more name, that is Shepherd's method. Shepherd's method. It is named by the name of Shepherd. This method named as Shepherd methods by the name of the scientist Shepherd. So this is about the k nearest neighbor algorithms. We are going to know about what are the remarks on the k nearest neighbor algorithm, that are in the next video. So today what we covered means, we started with the k nearest neighbor algorithm. What is the measuring technique? We are to apply the nearest neighbor technique to achieve the instance based learning. What are the measure we are considering? Euclidean distance, first one. And we can have the two types of target functions, discrete valued as well as continuous valued. For that, little bit different formulas we are using. This is first measurement, whatever to find the nearest neighbor is Euclidean distance. Here formula is shown like this, and there are depending upon the K. Depending upon the K, what is the K means? How many number of training examples, near training examples you need to consider to classify the new instance. That is the K value. So if K value is 1, 1 nearest algorithm we can say. If K value is 5, that we can say 5 nearest neighbor algorithm. To understand that, we took the figure and we classified the new instance, and also we learned about the Voronoi diagram. What is the Voronoi diagram? That is the diagrammatic representation for the one nearest neighbor algorithm in the form of like this polyhedron, polygon symbols, or we can say polyhedron symbols to represent that one and to find out the nearest neighbor one training examples. So this type of diagram we can call as a decision surface diagram, we can call as a Voronoi diagram. And what is the algorithm? Step by step procedure we said. That step by step procedure also we saw in this video like this for the K nearest neighbor algorithm. So this one is also important. And we saw the formulas for the discrete valued one, and also we saw the formulas for the continuous valued one. After that we learned about the distance weighted nearest neighbor algorithm. First we find the nearest neighbor algorithms by using the measurement of Euclidean distance. After that we applied the one more type of thing, distance weighted. Depending upon the distance we assign the weights for the every training example which are nearer to the query. Depending upon that also we can find the nearest one and we can classify the new query instance. And to find that weights, here it is the formula it is used to assign the weights for every training examples. If you are considering all the training examples to classify the nearest to classify the new query instance, then we can call as a global method. And global method also has the another name, Shepard's method. If you are considering only the nearest training examples, then we can call it as a local method. So this is what we learned in this video. Next video we are going to know about the remarks on the K nearest neighbor algorithm. By this I am closing this. Thank you. We'll meet in the next video.